So it's a great pleasure to be here today. Thanks to the organizer. Thank you all to be here. Today, I'm going to talk about children's drawing as a tool to study compositional thought. All this is preliminary work I've been doing with Théo, Marie, and Stan Dehaene and Eurospin. So this is ongoing work, not published yet. So take it as an opportunity to see the science, the ongoing science that is being done in our lab. And of course, we were happy to take any feedback, comments, or questions you might have at this stage. So just let me introduce very briefly the main idea of the use of patterns in the literature, because when we talk about drawing and the kind of drawings I'm going to present to you, you will see that we mainly refer to patterns. And when it comes to patterns in the literature, we see a lot of building blocks. These are often used to study patterns understanding in children. For example, children might be presented with a blue building block followed by a yellow one, a blue one, a yellow one, and then asked to prolong the given pattern following the underlying rule. The same applies to different sounds that might be serially presented to create auditory patterns. And again, children might be asked to mimic or to prolong or to extrapolate from the given sequence. When it comes to patterns understanding of this sort, we know quite a few things about the developmental trajectory of their understanding. So we know that at 3 years old, for example, children can copy a given pattern. So here you can see a star followed by a circle and then a star. And if a child is given a star and then asked to complete the pattern, is able at 3 years old to use a circle followed by a star to copy the given pattern. At 4 years old, they can copy much more complex patterns, such as, for example, the ones following rules such as ABAB or AABB or ABB. And at 5 years old, they can even transpose the pattern using different items from the given one. So if they're presented with one red square followed by a blue one, a red one, a blue one, and then they're provided with a star and a circle, they know that they should use a star followed by a circle to correctly follow the same ABAB rule that was used with the red and blue squares. But what about going beyond these simple patterns? Because using building blocks to study patterns understanding has one huge limitation, which is that they can actually overload the working memory pretty easily. In other words, can children understand complex patterns and can they composite several functional properties? Concretely, our questions are, do they understand the accelerating nature, for example, of an exponential function as opposed to a linear increase? Do they understand periodic patterns? Can they compose several functions together? And I think, and I hope it's pretty clear that using building blocks might be problematic to study these sort of patterns. So that's why we turn our attention to drawing, and probably you are familiar with this sort of games and exercises that are proposed in kindergarten and primary school by many teachers, in which you are asked to follow a certain path and to continue the path using the same pattern. And that's exactly the thing we ask to our to the children of our studies. So we investigated these drawing abilities both in 5 years old, so in kindergarten, and 6 years old, so first graders. And we present to them several types of functions. Here I'm giving you examples of linear and non-linear functions, but there will be also periodic functions later on in the presentation. So here you see the sort of thing that the children would see. So for example, a linear function or a quadratic function, exponential function, always starting with a red point, followed by a certain gray path. And children were asked to use a red marker to start from the red point, to draw on the gray path, and then to continue the path as they wished. And what I'm going to present to you now are the prolongation, all the prolongation that have been done by the children in our study. And as you can see here, despite a few exceptions, most children can actually distinguish pretty well linear from nonlinear functions. You can see, for example, that on the top left on the screen, the linear functions goes pretty straight, whereas for the quadratic and exponential, children use a certain acceleration. In other words, they are distinguishing that a linear function goes straight, whereas the quadratic or exponential ones do not go straight and have a curvature. Another way of looking at the results might be to see what are the properties that are respected for each function. So on the y-axis, I'm showing you all the linear and nonlinear functions that were presented to children. And on the x-axis, you can see the properties. You can see that most all children, both 5 years old and 6 years old, could understand the first point position, which simply means that they could prolong following where they left, where the drawing stopped. Concerning the first point derivative, we see an increase in performance from 5 years old to 6 years old. You can see that the children at 5 years old had still some trouble avoiding making discontinuities, which is the meaning of the first point derivative, whereas in 6 years old, you can see that most of them were able to prolong the pattern without making any points of discontinuity. And same applies to tendency. You can see that most children, except for the exponential decays, can actually correctly infer the general tendency of the pattern, which means is it increasing or decreasing, and the non-periodic nature of the pattern, which means that they were correctly prolonging the pattern, most of them, without using a periodic pattern. Another way of quantifying the results is to see whether the children were correctly making curved prolongation given a certain function. And you can see here, they were almost never making curved prolongations for linear functions, but they were consistently more making curved prolongations for nonlinear functions. In other words, for functions for which a curved prolongation is actually expected. And that was even more the case for 6 years old children. What about going beyond linearity? Because so far I only presented to you linear and nonlinear functions. Are children able to extrapolate, to continue the drawing of sinusoid function, for example? What about sinusoid function that varies in amplitude? Are they able to understand that in frequency and amplitude, sorry, are they able to understand that there's a change in frequency here, in the length of the cycle? What about zigzags, for example, that are whose amplitude is held constant, or zigzag that has a decrease in amplitude, or zigzag that have an increase in amplitude? Are they able to extrapolate from these sort of functions? Again, the first thing I can tell you is that children respect most functions' properties. So you can see that they are able to correctly extrapolate the first points of the graph of the drawing, that their first point derivative is quite respected, even more so at 6 years old, which again means that they are able to prolong the patterns without making any discontinuity. The tendency is correct. And what's interesting here, you see the last column of both heat maps, is that most children at 5 years old can actually understand the periodic pattern that is used, which means that a sinusoid is correctly prolonged as a sinusoid, a zigzag as a zigzag, but they still make a few mistakes, whereas this is no more the case at 6 years old. In other words, in 5 years old, still most children understand the periodic pattern. If they correctly prolong the drawing with a periodic pattern, but they might choose the wrong one, whereas this is no more the case at 6 years old. They correctly choose a periodic pattern over a non-periodic pattern, and they correctly choose a specific periodic pattern as compared to the other periodic patterns they could choose from. We can also see here that children were able to distinguish between periodic patterns with different cycle lengths. So on the y-axis, I'm showing you all the functions that were used. So sinusoids with a cycle length of 10 centimeter, which means with a small frequency, sinusoids with a cycle length of 5 centimeter, and other periodic patterns with a cycle length of 2.5 centimeter. Then as you can see, both children of 5 years old and 6 years old, they were actually distinguishing them because they were prolonging sinusoids with a cycle length of 10 centimeter with a longer length of a cycle compared to periodic patterns with a smaller cycle lengths. What about the composite functions? Remember the functions that have either an increase or a decrease in amplitude. Again, children seems to be able to distinguish between them. Sorry, the title is not the correct one. What I mean here is that children were actually able to distinguish functions with different amplitudes. So, for example, you can see here on the left, for sinusoid with a decreasing amplitude or zigzag with decreasing amplitude, most children on average were making an amplitude change that was in the decreasing direction, whereas for sinusoid or zigzag with an increasing amplitude, they were making prolongations that were more in the positive directional change. So they were making prolongations that had an increasing amplitude, and same results apply to 6 years old. In other words, they were able to not just understand that the function was periodic, but also add a linear component that was making the amplitude going up, increasing, or the amplitude decreasing. All right, so before leaving the floor to my colleague Théo, just some interim conclusions about this section on drawing. We show, I hope it's a point that I try to make, that drawing represents a nice tool to study the understanding of patterns, and it might overcome the limits of classic methods, especially using building blocks. I hope I made clear that children seem to understand functional relationships, including accelerating and nonlinear ones. And I think this is nice because it shows that they already have, even at 5 years old, a quite large catalog of functions and functional relationships available. And lastly, that they can compose several functions together, and considerably more so when they start formal schooling. With that, I thank you for your attention, and I let the floor to my colleague Théo for the second part.
Sorry. Hi, everyone. I tried to be quick because we don't have so much time, but can you see it, everything well?
Yeah, I see everything.
Cool. So yeah, today I'm going to present another ongoing project that we're doing with Lorenzo, but also with Marie Lubino and Stanislas in the lab. And it's also a new tool to try to study the compositionality, no longer using graph and drawing, but music and graph. And I think that the best way to explain you the idea behind the project is directly to present you the task in itself and to ask you in some way to do it. So I hope this works, but I will play you a very short melodies, and then you will have to match, to choose which one of the 3 images best matches the melody you just listened to. So let me. So I guess most of you recognize this very famous melody, and if I present you the 3 different images, which are actually 3 different graphs representing 3 different mathematical functions, I'm sure most of you will choose the very first one, representing a linear relation, right? So you are able to automatically and intuitively map the melodies and with a visual stimuli, which is a graph here. But you do so because you kind of understand some kind of acoustic properties of the melody, right? You understand that the frequency or the pitch of the note within this melody is increasing with time, and you know that you represent this kind of evolution with this kind of graph with a linear function that is going up, right? So this could drive your intuition, and if you are also a musician, it would be even easier task because you are able to write or to read this kind of scores. And here I represented, for example, the score for this very specific melody. And if you regress the musical notes in this score, you actually obtain the exact graph that I presented just before. So what we want to do in this present project is actually to probe this intuition and to see if young children who don't have any kind of musical education are able to map a melody with a mathematical graph. And to do so, we are using the following paradigm. So at each try, you will listen to a melody that have been created from one of these 6 different mathematical functions. So for example, a stair, a constant, or linear function. And you will have to choose which one of these 6 graphs best match the melody you just listened to. The melody have some variability in terms of pitch amplitude or rhythm, and you will do a lot of trialing for each participant. So for example, for this melody, I think most of you will choose the zigzag pattern, which are both created from the zigzag mathematical function. So first of all, what we did is to try this experiment with a small sample of adults just to see if the task in itself is doable. And I will always show the same representation with the function, so the melodies that have been played to the participant on the y-axis, and the functions that have been selected by the participant on the x-axis. And here I first represent the diagonal, so we expect to be 100%, and it's kind of the case. So adults are close to the perfection in this kind of task. And if we perform a q-square on the whole matrix, we obtain something which is significant. So it means that it's close to the identity matrix. But for some kind of functions that have been played, so for some melodies, adults are not perfect and they do some mistakes, but actually it's not random mistake, and I will go back on these kind of things in a minute. But interesting part in this talk is the result for the kids. And first, so we tested both kindergartner and also first grader, and I represented here the result from 40 kindergartners, so around 5 to 6 years old, sorry. And as you can see already on the diagonal, the kids are not really good at this task. They are close to the chance level, and actually only one of the functions that have been played, the performance are above the chance level. And it's actually not really great, because they are more willing to choose the zigzag pattern, whatever the functions that have been played. And if we perform a q-square test on this kind of matrix, we don't see anything which is significant. So in short, kids at this age are not able to do the task, so they're not able to extract from the melody the mathematical function and to match it to the corresponding graph. Concerning the first graders, so 1 year later, I represented here only the diagonal, and what we can see is that they are a bit better from the kindergartners, and they are not really good at it, but actually 3 out of 6 of this of the functions that have been played are above the chance level, significantly above the chance level, and the 3 others are the very limit of being significant. And if I represent the whole matrix, I think we do see the diagonal emerging from the data, and it's also if we run, for example, the same kind of analysis as before, we also see something which is significant, meaning that this kind of matrix could be modeled by the identity matrix. So if kids at this age are better than the kindergartner, they're not really perfect and they're not really good at it. They do some mistake, but actually it's not random mistake, as I told you before. So for example, if I focus on this only 2 melodies, so either the pitch that increase linearly or decrease linearly, you do see that participants and children are not willing to choose the 2 last function. So they do understand that the zigzag and the constant pattern are very different from the rest, but they're actually going to swap, for example, between a linear function that is going down or going up, or a linear function and a stair function. And the swapping between these 2 is kind of not idiot, like, oops, sorry. Is not absurd in the way that representing a melody with increasing pitch as a linear function that's increasing from left to right or from right to left is kind of arbitrary. So if you don't know how to read, for example, or if you don't know how to read a graph, this is not really a mistake, the swapping between these 2. And the swapping between a linear function going down and a stair function going down is also not really absurd, because the functions that have been played, the melodies, are actually discrete notes. So it's kind of also makes sense to represent an evolution of discrete note by a stair function, right? So it's a mistake, but it's not really a mistake, if it's clear. So in order to represent this kind of invariance, we define orientation invariance, so the swapping between something which is going up or going down, the discretization invariance, so swapping between a linear and a stair function, both kind of invariants, and error in red, which are the real error in our paradigm, right? And if I represented the data I just showed you before like this, you do see a kind of evolution with age, with kids that are doing less mistake, and are more correct answer, but we do see that they are still doing orientation, discretization, and both kind of invariance, right? So in order to disentangle this kind of real correct answer and invariance answer, we design another paradigm, which is actually the same kind of paradigm but with a slight differences, is that instead of using a continuous visual pattern, we are going to use discrete visual pattern. So each point representing actually the pitch of each node. And if we try to do so, so it's very preliminary, we have only 14 first graders that did the task. We do so that they are performing the task very well and better than before, but they are not performing in the way which we're expecting. So they are not able to discriminate, for example, the linear going up and the stair going up. So we still have some stuff to understand in this way. And just to end this presentation, I would like to emphasize the fact that this was the very beginning of the journey on this project. And the end goal with this kind of paradigm is to study compositionality. And instead, for example, of presenting melodies that coming from 6 different mathematical functions and presenting graph coming from 6 different mathematical functions, we can present them as Lorenzo presented before, with 3 graphs that representing actually 3 zigzag pattern, but one with amplitude pitch which is constant, the other one with amplitude pitch which is decreasing, and the other one which is increasing. So that would be the next step we try to study, maybe first in adult to see if it's feasible, and next in kids. So with that, I would like to thank everyone for your attention, and I think we're going to take questions for both projects with Lorenzo now.